Today we're going to be talking about the crystalline structure of four different elements. First element is magnesium, which is a hexagonal, close packaged. The second one is nickel, which is face-centered cubic. The third element is indium, body-centered tetragonal, and the fourth element is antimony, rhombohedral. Magnesium and nickel form to make magnesium nickel, and indium and antimony form to form antimonium.
So starting off with nickel, it has a crystal structure of face-centered cubic. The coordination number, there is 3 layers total connected to each atom, and each of those layers has 4, so it would be 4 times 3, which is 12. To find the atomic packing factor, it would be the number of atoms per unit cell times the volume of one atom divided by the volume of the whole unit cell. And finding the edge length of the cube, you would do the right triangle, and the hypotenuse of that is 4 times the radius of one atom. And using Pythagorean theorem, that would come out to 2 times the radius times square root 2. Plug that in to find the volume of the unit cell. That would be this value here, 16r cubed square root 2. And then you plug that in to find the atomic packing factor into the formula, and that would be around 0.74. To find the theoretical density of nickel, first you have to find the mass of the unit cell, which is around 4 over Avogadro's number times the atomic mass, 4 being the number of atoms per unit cell. And you'd plug that in to density equals mass of the unit cell divided by volume of the unit cell, and that would be around 8.95 grams per centimeter cubed. Magnesium. Magnesium has a crystal structure of hexagonal close packed, and the coordination number for magnesium is going to be 12. Because on each layer above it there's 3 atoms, and below it there's 3, and then around it there's 6, so it would be 12. And once again, the atomic packing factor, the number of atoms per unit cell times the volume of one atom divided by the volume of the whole unit cell. So for this one, C is represented by the height, A is still the edge length, and you can represent that by this triangle here. And then the volume of the total unit cell would be the base area times the height. And then using geometry, you can find that the height is represented by square root 3 over 2 times the edge length, and the area of the base. Plugging that in, you would get 6 times 1/2 the area times the height, and that would come out to a value of 24 times the radius of one atom cubed times square root 2. And then plugging that in to find the atomic packing factor, that would be a value of 0.74 as well. And to find the theoretical density, first you find the mass of the unit cell, which is going to be around 6 atoms divided by Avogadro's number times the atomic mass, and then dividing that by the volume of the unit cell, you would get a value of 1.74 grams per centimeters cubed for the theoretical density of magnesium.
Hello, today I'm going to show this third step for the project. So we're going to show the direction 120 and the plane 111, and then I'm going to calculate the planar and linear density for metal A, B, semiconductor A, and semiconductor B. So first we have here, let me make this not a really crappy, oh yeah, now we're fancy. All right, so it's really hard. The 4 steps we got here. You got the 120. You first position it to the origin, so it's going to be 120. Next, you're going to read it in ABC. It's 1 is A, 2 is B, 0 is C. Next, you're going to reduce it to the smallest integer of everything, Well, the smallest integer is 1. Whoa, it's 1, 2, 0. And then you just remove the parentheses and added these things, colons, and no commas whatsoever. And that's the direction. Crazy. Anyways, now you read the family in terms of A, B, and C. This is A, this is B, this is C. Now you take the reciprocals of them. The reciprocal is you put it over whatever number it is. If it's already, well, this is already over 1, and you flip it. So 1 over 1 flipped is 1. Crazy. Now you're going to reduce to the smallest integer. We have 1, 1, 1 here. What's 1 reduced to the smallest integer of 1? 1. Crazy. And you put in parentheses. For some reason, no commas whatsoever. All right, here we got linear density. We got the equation up here. Linear density is equal to number of atoms divided by the length. So we got from my previous reference, we have this, but I did the calculations roughly. So the length you have to derive from what type of cell you're looking at, or unit cell. For like HCP, it's 2R's the length, BCT, 4R over square root of 3, and as such. But I'll go over one, and then I'll just quickly go through the rest. So for this one, it's just 2R, and then the edge length is just, you just fill in the radius, which this you just find out. Length is then this edge length times the magnitude of the direction, which is just 1 squared plus 2 squared, because it's 1 to direction. And then you count how many atoms you have along that direction. And with HCP, we find that there's 3 atoms. And then you use this equation, 3 atoms over that, 4.19 atoms per nanometer. And that's just per nanometer. And then we did the same. I did the same for all this. As you can see, you can pause the video, look. It's very fancy, I know. And that's linear density. Now, planar density, you're going to take the number of atoms over area. So this, you're going to find the equations for whatever thing. The easiest is to find online or use AI, but use it loosely. You don't want to mess it up. But for this, it's pretty much the same equations until you get to area, which this is all supposed to be area. Oh. Don't mind this. You didn't see this. Cool. So this, now you got the same thing, but for area, it's 1/2 times the edge length squared times the plane, the magnitude of the plane, which is 1 squared plus 1 squared plus square root of 3. And then you just count how many atoms you have in that direction. We found 1.5 for all of them. Ooh, ooh. And as you can see, you can pause the video. I found the planar density for all of them. Yup. That's all, folks.